Our next talk is on asynchronism in MPI Intra-Node Communications, and it's going to be presented by Dr. Hyun-Wook Jin from Konkuk University, Seoul, South Korea. Hyun-Wook Jin is a professor in the Department of Computer Science and Engineering at Konkuk University, Seoul, Korea. He's leading the System Software Research Laboratory at Konkuk University. Before joining Konkuk University in 2006, he was a research associate in the Department of Computer Science and Engineering at the Ohio State University. And he's an alumni of the group. I was really entertained to know this fact. He received the PhD degree from Korea University in 2003. And his main research focus is on system software for high-end computing systems and cyber physical systems. So welcome, Dr. Jin.
Thank you, Mustafa. I sent an email yesterday. Okay, while providing the slides, let me just start because we are running out of time. So today I'd like to discuss about asynchronism in MPI Intra-Node Communication. I'm gonna present a little bit about our recent results. And this work has been done with my graduate student, Purumso, and this work is supported by National Research Foundation of Korea. Great. Okay, great. Okay, my presentation will start with background on asynchronism, and I will focus on data copy and communication event processing in MPI Intra-Node Communications. So these operations are run in synchronously in existing implementations. So we modified these operations so that they can run asynchronously. So I'm gonna spend most of the time describing these modifications. Then I will conclude my talk. Let me start with the explanations about blocking, non-blocking, synchronous and asynchronous I/O operations. And this, I borrowed this figure from a well-known article in IBM Developer. And as we can see, there are 4 combinations. So let me explain one by one. So with synchronous blocking I/O, application blocks until the I/O system call is complete. And read and write system calls belong to this category. And synchronous non-blocking I/O here may not be satisfied immediately, requiring that the application makes calls repeatedly to await completion. So read-write system calls with on file descriptors opened with non-block flag operate in this manner. And let me move on to asynchronous part in which we're more interested. So with asynchronous blocking I/O, application checks the readiness of multiple descriptors by using either select or poll system calls before actual I/O calls. So this model is used in network server programs usually. And asynchronous non-blocking I/O, in asynchronous non-blocking I/O, application can perform other processing while the background I/O operation completes. So AIO implemented in Linux belongs to this category. I just want to point out that blocking MPI communication belongs synchronous blocking domain, and non-blocking MPI communication is actually asynchronous non-blocking category. So since now we understand the blocking, non-blocking, synchronous and asynchronous, now let's take a look at MPI internal operations. This slide shows the intra-node communication channels implemented in MPI. Usually MPI libraries provide two different communication channels called shared memory and memory mapping. The shared memory channel moves messages from source to destination via a shared memory. So there are two data copies for each message in this channel. And the memory mapping channel directly moves messages from source to destination without intermediate copies by means of kernel level support such as CMA, LIMIC, and XPMEM. So there is only one data copy in this channel. However, this channel requires memory mapping, which adds non-trivial overhead. So usually small messages that do not incur much overhead use the shared memory channel, while large messages use memory mapping channel. So these data copy operations in intra-node communications are performed by CPU. Therefore, CPU resources are wasted for communication, and overlapping of computation and communication can be hindered. We think that this problem comes from the fact that this data movement is performed in a synchronous blocking manner. So first, our goal is to introduce asynchronism to data copy. To do that, we implement asynchronous non-blocking data copy by exploiting copy engines provided by contemporary processors. It is expected that asynchronous non-blocking data copy can alleviate overlapping between computation and communication. Now let's take a look at another important operation in MPI. As we know, MPI progress engine performs busy waiting to check the completion of outstanding communications. This busy waiting can promise fast response in communication, especially in HPC system, where a core is dedicated to each pair process. This figure shows an example that the receiver calls MPI receive before sender, and then the corresponding sender calls MPI send much later. Therefore, the progress engine on the receiver side should perform busy waiting until the message arrives. Therefore, the longer the busy waiting time, the higher the energy consumption. So the busy waiting time can become longer due to non-uniformity of network latency, asynchronous semantics in MPI calls, and load imbalance. And we believe that this problem comes from the fact that busy waiting based event processing is belong to the synchronous non-blocking operation. So our second goal is to introduce asynchronism in progress engine. So we propose asynchronous blocking progress engine for energy efficiency by using signaling. From now on, let me go over the asynchronous non-blocking data copy and asynchronous blocking progress engine. So let me first describe about asynchronous non-blocking data copy. As I have mentioned, our suggested design exploits copy engines. The copy engine is a special purpose processor that can independently access memory and copy data. And modern processors such as Xeon and EPIC provide such kind of copy engines. So by offloading copy operations performed by CPU onto the copy engine, we can save CPU resources and improve overlapping of computation and communication. There have been several studies to exploit copy engines. However, they didn't provide support for collective communication. They have focused on mainly point-to-point communication or one-sided communication. So we aim at exploiting copy engines for intra-node MPI blocking collective communications, such as MPI Bcast and MPI gather. I will explain asynchronous non-blocking data copy in 3 parts. First, I will describe a basic copy engine-based approach. Then I will explain C-CPU hybrid approach to utilize both copy engine and CPU. And lastly, I will explain about our enhancements on CPU-based approach. As I mentioned, we target blocking, more precisely synchronous blocking MPI calls while exploiting copy engine in an asynchronous non-blocking manner. So there is a big mismatch between the semantics of MPI calls and underlying operation. So we need a mechanism to preserve the synchronous blocking semantics of MPI calls. To do that, we utilize the memory protection mechanism in a way that segmentation fault handler blocks the application process when it touches communication buffer before completion of communication. And also, there is another important issue of mapping between CPU cores and copy engines. There can be multiple copy engines in the same node, and each copy engine provides several channels. In our current implementation, we simply map CPU cores to a channel in a round-robin manner for each NUMA node. Okay, this slide shows the overall steps of basic copy engine-based approach. In the first step, communication buffers are locked and their descriptors are sent to leaf processes. This buffer locking is required to utilize memory protection mechanism. Then in the second step, leaf processes insert request, actually these are the DMA requests to map the channel. And in the last step, copy engine moves messages. So upper figure represents the MPI Bcast and lower figure represents the MPI gather. And these figures are more or less the same except the direction of the data movement in the third step. Currently, in current hour implementation, we just use very simple level 1 tree for the Bcast and gather. However, there exists only limited number of copy engines in the system. So the level of concurrency of data movement is lower than what we expect. So we use CPU as well to move data when lowering the overhead is more important than overlapping. So we think that lowering the overhead is important when a segmentation fault occurs. So we implement virtual request queue that fragments the DMA request into several chunks so that we can efficiently switch from the CE mode to the CPU mode in the middle of data movement. And also we have enhanced the CPU-based approach to improve the performance of CPU hybrid approach. In existing implementation, both memory mapping and copy operations are done on the receiver side. So in MPI Bcast, for example, leaf processes perform both memory mapping and copy operations. Since these operations are performed on different processes, we can easily expect that they can be done in parallel. However, it turned out that the memory mapping cannot be performed in parallel because this operation requires a synchronization for in-kernel data structure. So those operations are sequentialized. And also in MPI gather, these mapping and copy operation should be done on the root process. So these operations also cannot be overlapped. So we changed this design so that it can segregate memory mapping and copy operations. And these operations can be done on either sender or receiver. We have freedom of doing this. So in our current implementation of bcast and gather, the root process performs memory mapping and the leaf processes perform data copy. Okay, we measured our synchronous non-blocking data copy on an Intel NUMA-based multi-core systems equipped with 20 cores. And we compared default approach, enhanced CPU approach, and CPU hybrid approach. So default approach uses CMA, and the other use LIMIC2, modified LIMIC2. So this slide shows the OSU micro-benchmark results of MPI bcast. As we can see, enhanced CPU-based approach could improve the performance up to 67%. However, we cannot see the benefit of CPU hybrid approach. This is because this micro benchmark doesn't has computation that can be overlapped with communication. So in this workload, it is hardly see the benefit of CPU hybrid approach, obviously. And this slide shows OSU micro benchmark results of MPI gather, and we see the similar results with the previous slide. To analyze the benefit of overlapping, we inserted matrix multiplication in between collective cores and measured the overall execution time. So now we see the CPU hybrid approach could reduce the overall execution time up to 58%. And I didn't explain that the 0% in this graph represents the performance of default one. So these graphs show the performance improvement rate. And we see similar results for MPI gather as well. Okay, now let me move on to asynchronous blocking progress engine. Sorry, anyway, I'm coughing because of asthma, not because of COVID-19. So please excuse me for my coughing and don't worry about infection, okay? Okay, power management of CPU can be done with DVFS or core idling. DVFS provides different levels of voltage and frequency for operating processors, and core idling turns off hardware components of idle cores. P states and C states in Intel processors are the states for DVFS and core idling, respectively. And there have been several studies to utilize either DVFS or core idling to improve the energy efficiency of MPI. However, these studies didn't consider the support for core idling on intra-node communication channels. So in this study, we aim to provide a framework that efficiently supports core idling over multiple MPI communication channels. Especially we focus on intra-node communication channels such as shared memory and memory mapping mentioned earlier. And I'm going to describe asynchronous blocking progress engine in 3 parts. First, I will describe about our framework for energy efficient MPI, and then I will describe signaling-based asynchronous blocking intra-node communication. And lastly, I will explain about our design of integration with blocking inter-node communication. Okay, our framework provides interfaces to insert user-defined policy into MPI progress engine. So you can use either APIs or hooking of MPI calls. If you use a API, you can change user-defined policy at the runtime dynamically. But you need modifications of application. And also you can insert user-defined policy with the hooking of MPI calls. In this case, you don't need to modify application, but you cannot change the policy dynamically. But still you can use different policies for different applications. And these user-defined policy can utilize internal runtime information such as ranks, communication channel, message size, number of busy waiting iterations, current busy waiting time, last busy waiting time, and so on. So these informations are provided in a uniform manner and passed to the user-defined policy through the parameter. And we basically implemented our synchronous blocking progress engine by using signaling. Actually, we can use CPU-dependent assembly instructions to implement this design, for example, M8. And this kind of approach has been presented yesterday from Dell. But we decided to use CPU-independent methodology to implement our idea. And those can be timers, semaphores, and signals. And we decided to go with signals because it is easy to support callback functions and flexible enough to support the inter-node communication channel. And also we believe that it is able to leverage existing decision policies used in DVFS and co-idling approaches. So this slide shows the signaling points of shared memory channel. We assume that messages that use shared memory channel is delivered over eager protocol. And basically we generate signals for every messages arrived. In addition to that, we also generate signal for some cases. For example, when shared memory is full, the sender may be blocked because it cannot send any more messages. Then if receiver consumes a message, there is a space to send more message. So then we signal to wake up the send processes. And this slide shows signaling points of memory mapping channel. And we again assume that messages that use memory mapping channel is delivered over rendezvous protocol. And in addition to the actual messages, there can be control messages such as CTS, RTS, and FIN. So not only the actual message, if we receive these control messages, we generate signals. And our framework also support the inter-node blocking inter-node communication. So MPI 2 is already implemented blocking inter-node communication, and you can enable it by using MVU's blocking flag. And this feature is actually implemented based on completion channel provided by network adapter. So we manage this signal for intra-node communication and completion channel for inter-node communication by using file descriptors in an integrated manner. And we check whether the state of file descriptors is changed by using epoll. In this way, we can apply user-defined policy for both inter-node communication and intra-node communication. So we measured performance of our asynchronous blocking progress engine on two ARM-based multi-core systems which are connected through InfiniBand. And we compare our implementation with the default blocking mode, and both are using CMA. So this slide shows the OSU microbenchmark results of MPI All-to-All, and as you can see, our framework could improve the execution time and energy consumption more than 40%. We think that this result is quite interesting because we didn't insert artificial delay into this microbenchmark to exaggerate some kind of skew. So without those kind of artificial delay, we still could achieve the high performance improvement. And also this is ARM machine, so it is already energy efficient, and still we get more than 40% improvement. So these results encouraged us. And this slide shows the OSU microbenchmark results of MPI All-Reduce, and we get more than 28% performance improvement here. And also we measured we ran the NASPERAL benchmarks, and here we get like 15% performance improvement for both execution time and energy consumption. Okay, let me conclude my talk. Today I explained about our asynchronous non-blocking data copy and asynchronous blocking progress engine, and some of the results are published through the papers. So you can see, take a look at some more paper through these papers. For future work regarding asynchronous non-blocking data copy, we need to support other collective cores, including blocking and non-blocking collective communications. And also, we need to integrate this implementation with inter-node communication. And regarding asynchronous blocking progress engine, we didn't have many policies yet, so we need to implement various policies to show the benefit of our framework. And also we are planning to measure the performance of real applications. And third bullet should be co-workshop with NowLab in OSU. Okay, thank you.
So thank you. This is a very nice talk. So I have a question for the co-idling in the asynchronous copy engine slides. So you mentioned that it's you make an example of Intel's processor. So does this feature has similar support on other architectures of processor?
Yeah, actually we used very, let me see the, yeah, oh, not this one. For copy engine, we used a very old machine. It's a Haswell processor. So we didn't have many physical copy engines on it. And we heard that some new recent machine processors have more number of copy engines. Then we can get more benefit from that. So we are thinking to use some newer machines, but still we don't know how many physical copy engines are there. We need to check, but at least what I heard is that newer machine processor may have more number of copy engines.
Yeah. Another question about the memory mapping engine. So is it using XPMEM, or are you comparing your methods with
Okay, currently we didn't compare with XPMM enabled MBAP. So currently for a copy engine, we use the MBAP that uses CMA. And for the energy efficient one, both our implementation and MBAP use CMA. So currently we didn't compare with the XPMM based version. Okay. Maybe you can explain if it would provide better overlapping or mm-hmm. Okay, thank you.
Yeah, hi, thanks for your talk. So in the C CPU hybrid approach, how do you determine the split of CPU versus the copy engine? Like it depends on the amount of compute, right? Available compute. So is that dynamically done or?
Actually, we don't use both C CPU at the same time.
Oh,
First,
okay.
we try to use copy engine, then switch it to CPU if application try to use the communication buffer.
Oh, okay.
So currently we don't pipeline across the C and CPU at the same time.
Oh, okay. Okay. Thank you.
Okay,
All right, thank you very much.
We're going to Ashok next on codes. Hello, yeah. I think we did a little bit of swap. I think yesterday I indicated like